The next concept what you're learning is the mean free path. Now, this concept is quite important to understand. Okay, now to understand mean free path, what exactly it is, we have already discussed this before in the previous videos. But still again, suppose if you have gas molecules moving around in a place, in a container, okay, the distance it travels between the two successive collisions. This is what we mean by mean free path. Okay, now let's try to do this mathematically. All right. Now what we'll do, let's say lambda is the mean free path. We'll try to calculate lambda value. All right. You guys can see in the figure. Now in this particular figure, you have to understand couple of things before we actually go about it. All right. Now what we'll do, say lambda 1, lambda 2, lambda 3, all these things are the path traveled, or you can say path traversed, whatever it is. So what do we have? Lambda 1 plus lambda 2 plus lambda 3 till lambda n is equal to C bar into T. Now that C bar is the RMS value. Alright. So lambda is what? It's the mean free path, right? So summation of all these lambdas divided by n, or C bar into T divided by n. Now D is the diameter of each molecule. Now see what's gonna happen if another molecule comes within this D, then for sure there is a collision, correct? So whatever we are looking at has to be in terms of D. Now C bar is what? It's the average speed of the molecule, right? So whatever volume we are taking, volume, it's gonna be pi d square into C bar into delta T. Delta T is what? Delta T is the time, isn't it? Now N be the number of molecules per unit volume of this particular gas. Okay. Then total number of molecules is going to be what? In that particular volume into the value of n, which is going to be pi d square into C bar into delta T into n. Now, if I calculate the number of collisions per second, what am I going to do? The total number of molecules at whatever the collisions you have divided by T, right? T in the sense delta T in this case. So, what we are going to get is n pi d square into C bar. Make sense? Now, let's take the average time. So average time, we'll call it as tau. So tau is equal to 1 divided by n pi d square into C bar. So the mean free path is what? The distance. Mean free path is what? Lambda is equal to C bar into tau. Okay, which is C bar into 1 by n pi d square into C bar. C bar cancels. So we get lambda is equal to 1 divided by n pi d square. Now this gives you the mean free path. Suppose if we do the exact treatment, okay, for this one, because here we are taking that it's an ideal gas, and we're also taking a lot of other assumptions saying that it's going to interact with only one molecule at a time. But then that's not the case all the time, correct? Suppose if we do the exact treatment as whatever it is in the particular gas, then lambda is equal to 1 by root 2 pi n d square. This is going to give us the value of the mean free path. In the sense, if between two successive collisions, the path whatever it is traveling is 1 by root 2 into n pi d square. Alright. So if you can understand, more the number of molecules it has, then lesser is the value of the mean free path. It's quite obvious, right? Isn't it? Because more number of molecules or more number of particles, then the distance between the two successive collision is to reduce, and it will reduce. So lambda value will be lesser if n value increases. Alright. Now, where are we going to use this mean free path to understand? To give you a simple understanding, this concept we use in understanding diffusion, viscosity, thermal conductivity. There are lots and lots of examples where this mean free path is important. Okay, even in certain electrical concepts, we use this mean free path. Understood? So, mean free path tells you by what distance it's going to move before it collides. Alright, so this is mean free path.